Now we're going to move on to the third approach, which is regression splines. And this is kind a combination of the two approaches that we talked about before. We're going to kind of add what we did with polynomials and fit essentially a different polynomial for each different chunk or cut for our x. So we're going to have to divide our range of x into, again, k distinct regions, and then within each of those regions, we're going to fit a different polynomial function to the data. So these polynomials, though, are constrained so that they kind of join smoothly at the boundary regions, or we call them knots when we talk about splines. Now, provided that the interval is divided into enough regions, this can produce a really flexible fit. Now, you have to be careful of that because you don't want to allow your model to overfit based on the data that you have in your sample, right? So the point is that if you took your model to a different sample, would you end up getting the same result? Probably not, because you've implied such a functional form that is based on the data that you have at hand in your specific sample. For example, you can think of cubic splines. So there's nothing too complicated that's going on here. We still have the same polynomial transformation that we had before, where we have x, x squared, and x cubed. But again, we're just allowing for a different polynomial to be fit for each of those different sections. Now, you'll see that this is pretty easy to implement in R. We're just going to use the BS function, which generates different base functions for splines with the specified knots. Now, by default, the cubic splines are the ones that are produced, so we could just go ahead and do that. We just have to put in what knots we want. And I'm going to just say that we want our knots to be at 40 and 60, and we want degree equals 1 because we don't want to overfit the data here. And I'll show you what that looks like when we change that. Now, degree equals 1 looks very similar to what we got with the polynomial transformation. And in fact, you can see the smoothing here is quite rough, right? We basically have one linear regression here, we have another linear regression here, and another linear regression here. And that makes sense because what we're doing is the degree is setting essentially the polynomial expansion that's happening at each cut. And so degree 1 is literally just a linear regression. Now, if you did degree 2, that would be a squared term. Degree 3 is cubed term. So we could do that where we have degree equals 3. And what we end up getting is something that looks even more close to what we would have gotten with the polynomial transformation. We could also use these things called smoothing splines, and they're very similar to regression splines, but they're different because they have smoothing splines that have different knots at different points in the segmentation of our x value. So you could imagine, right, when we have low n, or degrees of freedom here with our smoothing, you can see that it's generally quite curved, right? But if we allow for more knots, if we allow for 16, then we allow a much more oscillating fit that you can see is really trying to fit the data within smaller truncations of within our x range. So the way that this is doing it is within that region, it's minimizing the residual sum of squares subject to some type of smoothing penalty that again is setting the knots, right? So if we have a smoothing penalty of like 6.8, you can see that it's much broader than allowing for 16 knots where we have a bunch of wiggling around that is chasing data. Finally, we have these things called local regression or Loess smoothers, And they are very similar to the regression splines, but differ in one important way, and that is that the regions are allowed to overlap. So they do end up having a much more smoothed curve than the lines that we saw in the previous slide. So the way that we can do that is we can literally fit a Loess model, and here we're just changing the span, which is, again, just how much of the overlap is allowed to be smoothed. And you can see here that when you allow for a larger span, that's going to increase kind of the distance of that region that needs to be smoothed over. Whereas if you have a smaller span, again, you're going to get smaller truncations in your X, and it's going to wiggle around more and chase the data. To wrap up, in this module, we talked about how to incorporate different types of transformations for nonlinear associations between a covariate and an outcome. We talked about using polynomials as well as splines in our linear regressions. And next time, what we're going to do is we're going to talk about extending this. Instead of having splines or polynomials for one of our predictors, we're going to have multiple predictors. And in that case, we're talking about a generalized additive model, which you can imagine where we represent our different covariates all as different functions potentially that are nonlinear.